Hello everybody. Today we will continue from where we stopped last time. We were talking about the recurrent neural networks. I think we will have today a number of presentations. Let's check this now to see which ones are there. Okay, this is my okay. And paper presentation stuff is here. Okay, so today is 30th. Okay. Here I have how many people?
Actually, I performed my presentation today too. It was past week.
There is supposed to be one more.
Yeah. What is your name again?
Mehmet Selman Yücel.
Enes Selman.
Mehmet
Selman. So you did. Okay, you are good.
Hocam ben de yapmadım ama sunumu.
Başak sent me an email. She said that she won't be able to make it to the course. So we will take Mehmet Selman and Melih Doğancı, right? So let's take
Hocam
Başak out.
ölüyorum ama ben de verdim. Said Osman Karcıoğlu.
So Said, what are you saying?
Hocam ben sunumu
Said,
yapmadım.
can't you talk in English?
I didn't make my representation.
Why didn't you do last week then?
I didn't understand.
Why didn't you do it last week?
Last week we will gathering 5.46 and
Oh yeah, I had to leave. Okay, so maybe we can take your presentation for this week too. So let me take Başak out of here. Okay, let me put it in here. Okay, and Mehmet Selman will be the other one, and as third one, Said Osman is going to be making the third presentation. Okay, so we will have 3 presentations today. Okay?
Okay.
Good. So I will start lecturing today, and 10 minutes for presentation for each presentation. So Melih, are you here? Melih Doğancı, Melih, are you here? Mehmet Selman, how many minutes are you going to take?
Melih seems to be online. Melih?
10 minutes is enough.
10 minutes for Mehmet Selman. How about Osman? How about you? How many minutes do you? Said Osman,
I am ready.
how many minutes is your presentation?
One.
How long?
How long? Maybe 20 minutes, 15
Okay,
minutes.
15 minutes is okay. So it's going to be. How about Melih? Melih, are you here?
Melih seems to be online, but he's not
Responding. So maybe we are going to take maybe 45 minutes for the presentations.
I am here.
So how long is your presentation going to be?
20 minutes.
Okay. So let me do 1 hour of lecture, then we will do 1 hour of presentation, then another hour of lecture. Okay. That's what we're going to do. Is that okay? Okay.
So first hour lecture and then presentations and then lecture again?
Yes.
Fine with me.
Okay. Okay. Let me start doing the a little bit overview maybe first. Let me get rid of the annotations that we did before. Clear all. So we are talking about the recurrent neural networks. Okay, maybe, well, let me keep those annotations. Can I keep them now? Really? Can I keep them? Yeah, it is it. Remember what we did last time? We said that making a decision on if it's going to be sunny, cloudy, or rainy, okay, by looking at a single day's input is nice, but it is not sufficient. The nice thing is, let's look at a number of days data, okay? So one solution would have been just input all that data to the network, which makes the data, your network a lot larger. Also, we don't know how many days we are going to look back. The other solution would have been the recurrent stuff like this one. Okay, we keep our internal state from the previous run of our network, and we update our current state with the current data. So I am always paying most attention to the current data, current input. Also, I am affected from the previous decisions of this network. Okay, that was called the recurrent neural networks. There is something repeating itself, and this is something that we liked, and it works very well for sequential data such as natural language words or sequence of observations such as the temperatures and etc. Okay, so that's called the RNN, and we looked at the RNN. Let me skip these parts. We already did that. And backpropagation through time is the way to train these kind of networks. We learned about that, and there was a problem with this approach. Actually, this vanishing gradient, always a problem for these RNN, because if you unroll your network or if you backpropagate too much through time, then you will run into backpropagation vanishing gradient problems, and we have to find a solution for this. And later today we will see what that solution is. And later then we said that since RNNs are very popularly used with the natural languages, we spend some time with the natural languages, language models, neural language models, and etc. Okay, skipping this part. And we said that usually we use word representations, okay, to input our words to our networks. What's a word representation? We like to represent each word by a vector, a meaningful vector. The vectors are such that if two words are close in terms of their meaning or in terms of their syntactic functionality, their vectors should be similar too. That's what we said last time, and we looked at how this thing works, and this was the simple, like it was the autoencoder network. Okay, you input your words from one side and you try to get the context word or the center word from the other side, and your internal representation becomes your word vectors for each word, and it works very well. We talked about this, okay, and we call this word to vec, and vector algebra with the works very well, and it's actually surprising. We looked at those, okay, and what else? Okay, so let me skip these parts, and then we started looking at this picture. I think we stopped at this point. We said that now it is possible to have these kind of networks with the RNN structures. Okay, this is something we already did before, one input, one output. And this one, for example, the image captioning, you give one image, and we are going to see examples of this. We are going to give this input, and we will expect many outputs from a single input. So one example is image captioning. We give an image to this network, and we get many words out of this network. The other one is many to one. I give you a sentence, I like ice creams, and at the end I am expecting, is this a positive sentence, negative sentence, or neutral sentence? That's the other thing. This many to many is, okay, both of them are many to many. Okay, both of them both of them are many-to-many. This one is special for things like machine translation. You take a sentence of, let's say, 15 words in Turkish, then I translate it to English in 10 words. So I don't know the number of inputs for the input sentence, and I don't know the number of outputs for the output sentence, and still it's a many-to-many. And the number of words as input and output are certainly could be different. And this kind of many-to-many makes the decision immediately, like frame level image labeling, okay? At this frame, the person is jumping. At this frame, the person is walking. At this frame, the person is sitting, and etc. Okay? So we are going to look at some of the examples of these. Machine translation and video classification on frame level. Okay, so that was the basic structure of the recurrent neural net, and X is input to the RNN. Inside RNN we have our structure like this. Okay, so from our old state we merge two vectors, the input vector and the old state vector, and we pass it through this function, nonlinear function such as hyperbolic tangent, and we obtain our new state. This becomes our new state now. This is not our output, okay, but it's our new state, okay, and we keep using the same function for the next input too. So same function and same weight set is going to be used all the time for all the inputs. And our output is calculated using another weight set, but again, for this network it is fixed. So we have three sets of outputs, okay. We have three sets of weights. One is the weight that I use for the input vector. Remember, this is a vector. This is a vector of size m, and this is a matrix of n by m. Okay, so if I multiply this matrix with this vector, I am going to obtain another vector, right? What would be the size of the vector? What is the result of this multiplication? What would be the size of the result of this multiplication? N, right? So I would get a vector of size n. Okay, so this is one, and this is another one, another set of weights here, and this is my internal stuff, and I put them together. By putting them together, I mean I merge them, okay? I don't add them, okay? This is merging. Merge. I have one set of, I have one vector and I have another vector. If you put, if you stack them together, you would get one large vector, and you pass this through. Or did I? No, this is not correct. Is that correct? No, that's not correct, no. I definitely add them and pass them through this hyperbolic tangent. That's normal addition, it's not merging. Okay. Well, it's almost the same thing actually. Add them and it will be our new state. And using our new state in a third set of weights, I can calculate my outputs. Okay, so this is the vector before my output. Of course, I need to run some kind of a softmax function, something like that, to get my final output after this. Okay, and computational, sometimes we express this using this computational graph. X1 is the first input. Okay, I feed it through this FW along with H0, and I get H1, and then X2, I feed H1 and X2 feed through this FW. These two FWs are the same thing, and I get this, and it continues like that, okay? This W weight matrix is common for all of this stuff. Okay? So that's the idea of RNNs. We keep using the same weight for all the rounds of the same network with different data. And of course, every time I get a new state, I have one output vector. Okay, those are the y's. Remember, to calculate the y, I need another matrix. That's what that. And using some kind of a softmax function, maybe the softmax function itself, I can get the labels or the classes for each stuff. Okay. So this is how okay, many networks work. Many. This is how the many-to-one networks work. Okay, you get one final result out of the final last internal state. This will be your final output. Or sometimes I do this. I just combine them all together to get one final output. Many-to-one. Okay, good. Sometimes I do this. This is called a very popular network that is used with the RNNs. It is called encoder-decoder networks. This is how it works. Very similar to many-to-one. Okay, you give your input to this network every time you update your internal state, but you don't output anything. Okay, you don't output anything. So it looks like so far it looks like a many-to-one network, but we don't update anything. We don't output anything yet. Then when our input is done, when we are finished with giving the input, okay, we start producing outputs with a different weight set. So we switch the weight set. Now it is different. So this part is encoding some kind of a internal state, and this part is okay, decoding some kind of internal state. So this is gathering data from the input, and this one is learn everything from the input. Now it is producing stuff. So this is the encoder part, this is the decoder part. So encoder-decoder structures are very popular with the natural language processing researchers, because you give your complete sentence, you ask for the translation. You give your complete paragraph, you ask for the summary of it. You give a complete paragraph, you ask for the paraphrase. You ask this network to paraphrase your original sentence, and etc. So this kind of many-to-one encoder-decoder structure is used in many places. Okay, so let's look at this example. Character level language model. This language model is very simple because it doesn't depend on the language itself. It doesn't know what kind of language it is using. It could be Turkish, English, French, Japanese. As long as you can represent that language using characters, this will work. Okay, so and I will represent each letter by a one-hot encoding system. So I like to input this hello to this system. This is what I am doing. Okay, I input this H. Okay, this input is multiplied by this input matrix. Okay, and I multiplied my WHH with my previous internal state results. At the beginning it is all zeros because I don't have the previous one. And apply this hyperbolic tangent and I get this one. Okay, so and I give this E and I get this L and I give this L. It goes that way. But what are we doing? I mean, we don't have any results yet. Well, how are we going to calculate the loss? Because this network is not producing anything. Without producing anything, this is not trainable. This is not a network that we knew so far. This is what we are doing. It's very simple. When I give you an H, it is supposed to produce an L. What did I do? Can I come back? I think it is around here. Yeah. When I give you an H, you are supposed to produce an E, and I give you E like this. Take it E, okay, like that. And you are supposed to give me an L, from L, another L, etc. So as you see, training this kind of network doesn't need any human labeling. It is already just give a sentence, get a sentence, get sentences of millions of words from Wikipedia. Okay, I have to take this, sorry. Efendim? İyi günler. Teşekkürler Nadir Bey. Şu anda dersteyim. Ben çıkınca arayayım mı sizi? Teşekkürler. Geçersiniz. So this is how you train it. So training is not free, of course, but the label data is free because all you are doing is you are asking your network to guess the next letter that I am going to read from the keyboard or from the Wikipedia dataset. If I do this, training is easy. After I trained it like this, okay, I can write my loss function that way because I know what I am going to produce, okay? For H, I am supposed to get E. For E, I am supposed to get L. For this L, it is that one. You might say that, how about this one? Yeah, I am telling you, you might say that, you are telling me this. When you input an E, output should be an L, okay? When this input is E, output should be a space. Isn't that contradict? Doesn't this contradict with each other? What do you say?
We have previous state also.
What's that?
We also have previous state.
Yeah, well, that's the nice thing about, exactly. That's the nice thing about the RNNs. We don't depend on our current input only, okay? What happened in the past is important too, okay? Here in the past, an H was input. Here in the past, all of these characters were input, okay? So what are we going to do now? We are going to train our system like this. Remember, this internal state depends on the previous state, and which depends on the previous state, and it goes that way. That's the nice thing about the RNNs. And if you train it this way, your loss function will be very complicated because the difference between this E and the output, difference between L and the output, and so it is becoming more and more difficult. And your gradient data from here, your loss will run through all the way there, etc. So it will be more complicated. That's why we don't train our network that way. We do this truncated back propagation through time, okay? So we only do this maybe for 7 inputs and 7 outputs. So our input and output are conveyed in a computationally efficient way. So it is efficient and it is doable. No memory, large memory requirements. The problem is though, I cannot go much back, okay? This loss will be affected from this output and this output. I cannot remember the things that happened way back, okay? So this is a windowed truncated back propagation through time. It is efficient, but it is missing lots of stuff. We have to find some solutions for this. And we skip this, we slide this window in our network, in our input, from left to right, and we keep repeating the same thing over and over again. Okay? Truncated back propagation through time is the thing. Okay, so if I train such a network, so what am I going to do with this network? I can do this experiment. I can start, I'm going to give this letter S, and I would expect something to be produced. Let's say it produced a T, then I took this T and gave it to here, T, okay, it produced A, and I gave this A as an input, okay, it produced another T, so it looks like it is producing something like station, okay. So this is one thing. The other thing is this, remember, this one is producing one hot vector, okay, and the largest value belongs to T, that's why I picked T, but I don't have to pick the largest output, right? Maybe this one has 25% output value score. Maybe some other character has 24%, right? I don't have to pick the top one all the time, okay? Pick a random one at the top 5 letters, and it's going to give you some other random words, not the same word, but some other random words. And if I train my network on a Python code, okay, this is what's going to be produced, what's going to be produced by this network. So it looks like a real Python code, okay. It does something, it looks like something meaningful, but it is actually, if you look at the stuff more carefully, I mean, the line seems fine, but some of the things doesn't make any sense, okay. Some of the variable names, it just makes this up, etc. And the same thing is for the Shakespeare again. It is just producing a Shakespeare text if I train it on the Shakespeare text, and what? And if I train my stuff on the LaTeX file source, and I can produce stuff like that, okay? A text that looks like a mathematical, a paper about mathematics, okay? And it looks like it has proof in it, okay? It has equations in it, and these won't work. Why? Because these are the label numbers, and label numbers has to be meaningful. LaTeX said that I can't handle these. But I mean, if you look at this, if you try to read this, it looks like really somebody tried to write a paper about something, I don't know. This is funny though. By algebra, lemma something, we can define a map of complexes, etc. So that doesn't make any sense, because I mean, it starts with some kind of a notation. It never talks about this anymore. This equation goes away. It doesn't talk about this equation, and etc. And the same thing is for, I think they trained it on this Linux stuff. Okay, looks fine now, but this will not compile, of course, because I don't think that there is a variable name state anywhere. Okay, I don't think so. And count, as you see, where did we define this count? It is either a global variable or it has to be a local. It is not local, so it's just making up stuff. It doesn't know the meaning of the statements.
Undefined variables.
What's that?
Undefined variables.
Yeah, undefined variables, but the variable names are just logical variable names. They make sense. And taking the and bitwise and with this count is okay. Okay, and the expression seems fine. The indentation is very good, right?
Yeah.
Indentation works fine. And when you open a, yeah, see, this one opens a curly bracket, and this one ends it. How about this one? Where does this start? Oh, it starts here for yeah. It knows about that, yeah. So it can balance stuff. How about this parentheses? Yeah, this parentheses is, yeah.
It's okay.
Balancing of parentheses are fine too. So the most mistakes are from it doesn't know about the meaning of variables. Okay, so just random code, Okay, so somebody said that why don't we look for meaningful state cells inside this RNN? Remember the RNN? Okay, there was an internal state, let's say of size 100. If I train this network on the Unix code, let's try to see what kind of things each neuron is sensitive to. Okay, that's the experiment. And in this case, just say that, okay, if my input is backslash, okay, it just picked one cell, say that if it is excited, it is red. If it is not excited, it is blue. Okay, so it looks like this cell is behaving randomly. I can't associate the behavior of this with anything. But if there is another one, okay, it looks like this cell is excited when it is out of the code. Okay, when it is inside the code, it is not excited, but when it is outside the code, it is excited. Okay, so maybe it's a code detection cell. And this one is line length tracking cell. So when you get close to the end of line, it becomes excited. This one is excited inside if statements. So, I mean, these are all learned without getting any of these kind of information from myself. What is this? Yeah, this is the code command cell. Okay, this is the command and code cells. So maybe it is meaningful. Code depth cell. Okay, if your depth is increasing and it is getting excited. So like the CNN networks, okay, remember with the CNN network, some of the nodes, some of the neurons are specialized for recognizing faces and the numbers and etc. Maybe we have the same thing for the RNNs too. That's what they are saying. Of course, since they are not about, this is not about, since this is not about visual stuff, making this kind of information sensitivity visual is not that easy, but still it works somehow. Okay, good. Any questions so far? How are we doing with the online people? Are they still there? I think I have, yeah, okay, good. I have some number of people, 10 people, maybe 8 people. Good. Okay, any questions? Farshid, why are you so silent today? Okay, so you are busy. He's at the airport or something like that. Okay.
Yeah, there was a situation that written on the metro side.
Okay, any questions? Let's look at this interesting application. We are going to combine RNN with CNNs. Our task is, remember, image captioning. One input, many outputs, one to many. This is what we do. We take this image, we run it through some CNN, for example, ResNet 18. Okay. We don't use ResNet 18 for classification, but we use it for the last vector. Okay. The vector just before the classification layer. So this is 4096 dimensional vector. Okay. And I feed that vector to my RNN as my H0. Okay. There are certain other solutions for those, but I am giving this as my H0. Okay. And then I say that during the training, you are supposed to produce straw, and get that straw, give it here, hat, get that hat, give it here, and produce end of sentence. And train thousands of images like this, okay? Give the image like that, and produce these sentences. And then what you do is, you get a new image, okay? You get a new image like this one. Give it to the network to ResNet 18, okay? Get the ResNet, is this ResNet 18? What is this? I think this is VGG, right? Okay, this is VGG, I guess. Give it to VGG, okay? Get this 4,000 dimensional vector out of here, okay? Don't use the last two layers. Get this one, and I am starting the network that I trained, and I get this as WIH, okay? Make it RA0, or the slide says that do this, okay? Slight modification. Our new H will be, previously it used to be our input times the input matrix. Our previous, well, this is supposed to be H minus 1, okay? And this is sorry, HT minus 1, and this is HT, okay? So HT minus 1 is multiplied with the internal state matrix. Input is multiplied by the input matrix, and run is 10H. Now I am not going to do that. I am going to do this. This one and this one is the same. Now I have this new matrix for this 4096 dimensional vector, and add them together and run it through this hyperbolic tangent and get your new state vector H, okay? And now this one is supposed to produce straw, okay? Okay, I get this, it is straw, it is supposed to be straw. I feed this straw again, it is supposed to produce a hat, and I feed the hat again, it is supposed to produce end of sentence sign, then I am done. Okay, so this image captioning application is as simple as this one. Get the VGG output, feed this to this RNN, and run the RNN on these test images, and that will be your result. And here are the.
Do we retrain VGG here?
No retraining, okay? If you have lots of data, maybe you could, but no. You just ignore that's what you do. You just ignore you just ignore the last two layers of classification. You just get it here, okay? If you have lots of images and corresponding captions, maybe you try to fix this part, freeze it. Maybe you try to train this part. You could try, but in this example, no, we don't. Okay?
Thank you.
So this is as simple as that, and it really works, and sometimes people don't believe it. I don't believe it, but I tried it and it works. And this is what's happening, okay? Good examples. I give this image and I get these sentences out. A cat sitting on a suitcase on the floor, okay? A cat is sitting on a tree branch. A dog is running in the grass with a frisbee, really. Just compete with noun phrases and everything, okay? So this one is interesting. Two giraffes standing in a grassy field. I mean, as an NLP researcher, when you look at the results, without knowing the structure of the language, I didn't do any parsing. I didn't say, these are the verbs, these are the nouns, and these are the stuff, etc., right? I never said any of them, but it still works. It's simply amazing. It is both scary and amazing. It is scary because what happened to my 20 years of research about language parsing and etc. That's why it is scary. and it is amazing because it works so well. Well, I mean, it makes some mistakes too. Okay, understandable mistakes maybe. A woman is holding a cat in her hand. Obviously, no. A woman is wearing somebody's fur. And a person holding a computer mouse on a desk. Well, I mean, it is not, but okay, how about this one? A woman standing on a beach holding a surfboard. Well, kind of, yeah, okay. So failure cases.
I remember Facebook was using that. When you can't see images,
Yeah,
it was showing a caption like that.
yeah. Google tried this one, and given the image, it was giving you some caption back, description back, and then one day they made a very, very bad mistake. I don't want to tell what that mistake is, but it was a very, very bad mistake, and they stopped it. Yeah, they are not talking about it anymore. Okay, so they changed their policy this way. They say that if I recognize a human on that picture, I am not going to talk about it. Google Lens works that way now. Google Lens, it works that way. I'm not going to talk about humans anymore. Okay, because doesn't matter if your precision, if your accuracy is 99.99999 correct. If you make one bad mistake, then all of them are garbage. Okay, so that's what happened. Okay, let me stop here. Let's take some break. After the break, we will continue. Maybe we can keep the break for 10 minutes. Okay, let's be here around 17:00, and we will get the presentation from our 3 classmates, and after that I will continue with image captioning with attention. Okay, 10 minutes.
So I also remember a tweet robot which is optimized for faves and retweets,
Yeah,
and it started to behave inappropriately. And
yeah.
they stopped.
Merhaba Nadir Bey. Kusura bakmayın dersteydim açamadım. Buyurun. Yok estağfurullah. Evet. Okay, we can, I guess we can start now. So we can start with you, I guess, right? Can we start with you? So are you gonna use your computer or my
Yeah,
computer?
I'm going to use it.
Your computer?
Uh-huh.
Okay. Come on here. I will turn off. You may share your screen, and I am turning off my voice and everything. Okay, good. It's yours. Are you connected?
Actually, how can I connect to this one?
No, you presented through Teams. Are you connected?
Oh, okay, I'm not.
But if you like, I can give you my VG. Do you have VG out? VG?
Yeah, yes.
VGA?
Yes, actually, I have.
Yeah. Okay. No, it doesn't have a VG.
Oh, yes, this one.
Okay. Nobody will see you if you do that. I mean, just, are you connected to Teams?
Not now, I will connect it.
Okay. Connect to Teams and do it that way. And
I want to see actually my note, hocam. So
What?
I want to see actually my notes in the presentation so I can use it.
oh, sure, yeah. Well, you should use it. Otherwise, we won't see it. And maybe come closer. I don't know. Let me take this out. Okay. The projection is okay. You are already projecting.
Yeah, I will try to do that. Hello everyone. So my voice is good, right?
Yes.
Okay. So my name is Salman. Today I'm going to be talking about the work entitled Cluster Net, which detecting small object in life science by exploding spatial and temporal information, which published in 2018 July. So when we look at the typical object detection problems, it was trying to detect a couple of objects like 3 or per image generally, and object nearly fill most area on the image. So as you can see, it's the typical object detection output, so which includes many, maybe not so many images, not so many objects it shows. But when we look into the much more difficult problems such as wide area motion images, so there are scales of thousands of objects per image actually. So also object size are nearly 0.000 something of the total size of the image, which will I show you. And nearly all the state art methods in wide area images were failed in these days actually. When they were working with challenging data and motion information in the form of background subscription were famous, and also they will show how they use this information too. And also in this work, they verified how bad fast faster RCNN and heat map based fully CNN, and they also offer a better two-stage solution. And one of them is the cluster net, also first stage. And when we talk about the first stage takes extremely large video frames, and it combines motions and appearance information with also again CNN, and it proposes the region of object of interest. They call ROI, region of interest. So this ROI contains several hundred of objects due to the frame size and object density. Let me show you. Okay, so before the data set, when we compare the object detection data sets, you know, Pascal and image network, and still most popular data sets. But when we check the wide area data sets, they called VPAFB, which I will talk about that. And when we compare these data sets in the Pascal and image set, you know, the blue one is the, let me check it again, so average object size. So in these data sets, the object in the images fill nearly 22 or 20% of the image, and also average number of objects in these images and 2 or 3. But in our data set, it's more complicated data sets, and the images fills nearly 0.00000 something 7% fills in the images, and also each images has 2K objects, and this concept will have actually has a solution to detect these type of images, not the original images, as we know, the custom images actually. So let's talk about the data set little bit. This data set is Air Force Research Lab data set, which created into 2009, and also single sensor, 6 slightly overlapping cameras were used, and area coverage, which you see in this area, is nearly 19 square kilometers, and the frame rate is 1.25. As you see, no color in these images, only black and white images. As you see, 315 million pixels per frame for each images, nearly this pixel size. And also average with vehicles 9/18 pixels. And you know, the data set is like that, so it's a little bit different than what we expect. And the main issue actually finding this blue one, even if we use our eyes, it's really hard to detect any object in the left side of the left side in this image, and we cannot recognize what is and where is the object. But this concept solve this issue too, and I will talk about how they solve this issue. And the blue one is the first stage, reducing the area, and yellow one is the first stage, reducing the area, and blue one is the second stage, detecting the object. And also there are some difficulties in this wide area motion images. So you know, we are taking the pixels, and sometimes we're missing the images which shown in the left side, and sometimes we are taking the frames, but for the second frames, images changing and blurring, or this kind of problems occurs. So this makes our work hard to do. And also the computer camera is important to these kind of data set. And I talked about that. It's the very small object, 9/18 pixels in size, and there is no color, so raw resolution and single channel grayscale images, also sometimes blur and unclear object we can see in these images. So proposed solution, there are two types of convolutional network, which first stage is cluster net and second stage is Fovea net. And the method effectively utilizes both spatial and temporal information, which in these days NOVAS actually was trying to do that, and we will see that most of the approaches were trying to just one frame, but this time we are using many frames, and they compared two or three or 5 frames with the training and testing. And this approach removes the need for competing background subscribed images, so which means these are the old computer vision techniques, and actually it removes to do these kind of stuffs. And again it does, but normally we need to give too much effort to this kind of things, but right now it reduces. Actually also in this solution 5 and 16% improvement for F1 score for the moving object, and also 50% improvement for the stopping vehicles. Yeah. Also the false positive rays reduces the 5.5 pixel to 2 pixels. So these are the good things in this solution. Also in this solution, the traditional computer vision techniques, I told you background subtraction and frame differencing was used, and we will mention that. So also region proposal network, the faster RCNN, they show why faster RCNN doesn't solve this type of problems. Actually it takes, the main reason, it takes only single frame, so no temporal info, and wide area motion imaginary is large, so it needs more power to train, because as we know, the faster RCNN goes the images shifting, and it takes too much power to do this stuff. And also spatial temporal CNNs too, I will mention it. And this is the general architecture of the cluster net and Fovea net. We can see how it works. Actually, it takes the images and it finds the region of interest, and it gives to the cluster net, and cluster net extracts where the object can be, and it gives the score. And also using the threshold, we are taking the images with threshold images. Actually, we are not taking all images and giving the input to the Fovea network. If we do, actually it takes too much time, but this threshold helps to train and test our wide area images rapidly, and this also good step for the wide area detection. And also you see the Fovea network, it's completely the normal CNN, 2 convolutional and max pooling, convolutional, and convolutional, and in the output it shows where the images. And the output is the Fovea network, and it's shown in the left side, and then we put these outputs into the original image, and we can see where the object, in the vehicle object actually. So it's easy to deconstruct the images again. And I will talk about the experimental studies and result a little bit from the paper. Okay. Okay, let me do that. Wait. Okay, I told we were using these data sets, and also before the goes into the first stage, there were used some techniques, and actually so many techniques, and they compared all the techniques in the results, we will check it too. It explains these things, and also these models were trained in the copy. They mentioned it too. And it says the cluster net uses stochastic gradient descent with Nesterov momentum. Base learning rate is 0.01 and base size is 8. And also decreased learning rate by a factor of 0.1 of upon the validation loss decreases. And in the second stage, Fauveya net uses Adam with a base learning rate of 0.01 and base size is 32. And training and testing was performed on a single Titan GPU again. And also I mentioned that the output was thresholded because in the Fauveya net part we are not giving all the outputs, and we are giving only the possible image, actually array of interest. And actually in the first stage it says to compute median and background subscription images for all frames following the method by real. So I can show the real, how is it? So you know the background median background, it shows image like that, and then it's applied gradient subscription, and the detection part actually is not used in this work, I assume. So actually we are using this concept in the data augmentation too. So also it helps in the localized or find the array of interest too. Actually, let me show the output little bit, the results. So they are creating a couple of, not data set, actually array of interest. So they are testing and training these array of interest images, and they use many concepts during this train and test part. Let me check it again. So before the last tables, let's check this one. Also you see the faster CNN output, actually how the result is that, recall and precision curve. And when they used 5-frame bitmap regression means the first stage, and it's nearly the same background subscription deep learning method. So actually they were trying to reach, and they were trying to show how good is this, the 5-frame actual effect of the frame. You know, you see the just 1 frame and 3 frame, 5 frame, it goes up and it gives good contribution. And also they compare all the techniques. So there are many techniques for the first stage. And we were talking about the Rayleigh, and Rayleigh method gives F1 scores. For example, let's see, for the first data sets 0.8, it's nearly the stable 0.8. But you know, they use many techniques, Sommer, Shih, Kent, or these kind of techniques, and most of them didn't give any result for typical data sets. And but when we check the cluster net, so it's highly good results, 0.9. Also there is no less than 0.9. Actually it was the main. So you know the traditional object detection techniques when we use, so it's easy to localize and find the images when we objects fill the images with a high percentage, but for the wide array motion imaginary, so it's hard to detect this kind of objects, as you see. So this concept solves this problem and gives good contribution to the science actually. So that's my part. If you have any question, I can answer.
I have a question.
Okay.
Does FOIANet output a bounding box for the object or only a point?
Actually it gives a bounding box, but let me find which I remember. So it puts the bounding paths and it gives the dot actually.
Hmm.
Yeah.
It outputs a dot.
Mhm.
It gets an area and
Yeah, yeah.
outputs a dot. Okay. So first stage
It's just reducing the
determines
area.
an area, small area,
Mhm.
and then Foveanet.
Yeah, Foveanet
Finds
takes
points.
and finds the points actually. And also first stage helps to decrease the images, you know, because it's a wide area and we are not want to give all the images to the network. So we are cutting the couple of images actually, possible images.
Okay, any questions
Why
from
they
the
call it
audience?
cluster net?
Yeah, would you
Hocam,
ask a question?
good question.
What is the question?
Why they call cluster net?
Yeah.
Actually, I was trying to make up because I'm not pretty sure about that. So, and it checking all the images, not all the images, and it checking all the possible area of interest. So it finds the high percentage of the location. For example, it checks the density. So in the end, it gives images with high density. So when we check the clusters, and clusters helps to make system always up. So maybe they gave this name. I don't know. I'm not sure about that.
But it's not a clustering thing. It's just the output is some sort of, let's say, object heat map or something like that. It's not actually, it has nothing to do with clustering, I guess.
Yeah, yeah. Maybe because of the concept. Do you know, Hocam?
I mean, my guess is that they don't know what cluster means and they're actually using something. I mean, they are not probably machine learning people, so they wouldn't have used cluster, something heat map net or something like that. I would have used it instead of cluster net. So, okay, thank you.
Okay, thank you, Hocam.
It says that it is because there are one or clusters of hundreds of objects. That's why, since it can work on these kind of data, they call it cluster net.
Hocam, I missed it.
So they say that it is supposed to work on clusters of hundreds of similar objects. That's why they are taking advantage of it. That's why they call it cluster net. Okay. If there are no questions, then maybe we can move it with the next speaker. I don't know who that was, but
Okay.
who is doing it next? Okay, I have it here. So, Mehmet Selman did this. Melih, are you there? Melih, maybe. Do you hear me, Melih?
Bilgisayarınızı takabilirim yanına.
Basma be.
Alayım hocam. Hocam mikrofonunuzu açayım mı buradan?
Hoparlör açsak yeter. Ya da ben buradan çekerim. Melih, do you hear me? Melih, it's your turn. Melih is not here, I guess, right?
Is your microphone open?
Yeah, I am connected here. So if Melih is not here today, for some reason he's not answering us, how about Said Osman? It's your turn, Said Osman. Okay, you can start sharing your screen and you can.
Okay, sure.
No, not yet.
Yes. Okay. Can you see, sir?
Yes, yes, we do.
Okay. Today, my name is we are gonna talking about the deep leaf segmentation using synthetic data. Our subject is that. First of all, I want to tell papers, motivational papers. The motivational paper is about the agriculture. How can we use more develop agriculture? How can we control consuming plants, plants water, less water, etc. Actually, I want to start with the some terminologic terms. The terminologic terms, first of all, CVPPP. It is saying us the plant phenotyping. Plant phenotyping is actually identification and evaluation of plants. We are using this CVPP for the identification and evaluation. And next step is we want to the leaves. We have to use leaf segmentation challenge. LSC. So we are using the Arabidopsis plants leaves. We are taking the images top to down, and we are using this CVPP plus LSC for the observing this situation images of plants. Next, we are checking how it works. Leaf instance segmentation labels is telling us give the background 0 and use the RNN to give the IDs and use the mask RNN for coloring. Next step is we are giving the synthetic data into machine learning, and we are taking the segmentation labeled plants. And how can we check this? We are saying that where XX is an integer number, and find out this solution, this result. Next one, mask RCNN. I want to show that, yes, this link. This link is saying us mask RCNN for object detection and instance segmentation. What does that mean? That means it's saying us I can give object detection. I am giving the IDs in the images object, and I can coloring instance segmentation with this mask RCNN. And next one is saying that we are taking the pictures, width and height is 550, and we are giving test 1 for the Z. As you can see, we are looking for the plants top to down, and we are using the mask RCNN, giving the color. Black is the background 0, the other leaves are 1, 2, 3, etc. It's going to true. And I want to show the example. We can give the IDs in the object, in the image object, as you can see. But it's more complicated. When we use mask RCNN, everything is more clarified for us, for machine learning. Anyways, we are going to deep leaf segmentation using synthetic data. As we can see, plant level measurements, we talked about that. We are using the CVPP for the plant phenotyping. And second one is the leaf level measurements. When we want to leaf level measurement, we have to use LSC. LSC. This one, leaf segmentation challenge. And we got a problems, appearance of new leaf growing because of we want to solve these problems. So we are using the machine learning because of we cannot wait the new leaf growing or appearance changing. So that we are using the synthetic data. We are generating the synthetic data from original images. And how can we using that? CVPP for phenotyping, leaf segmentation challenge, controlling the leaves, segmentation to leaves. We have Arabidopsis and Tabaka, Arabidopsis 783 pictures, Tabaka 27 real images. We are trying to augmenting the data with synthetic data. First, we are using CVPP, then leaf segmentation for the control leaves. The important thing is domain randomization concepts on definable objects. When we use CNN, we are using the kernels, then using the subsampling and taking the maximum values of important values. Then when we combine them in real world and in real data and fake data, we need to use domain randomization. Next one, Coco is using these images, ImageNet, etc. CVPP-LCS 810 images for training, multiple leaf instances. And there is an important thing here, single plant. We are using single plant and multiple leaf instances. We are taking the pictures from the top to top, only one plant. And approaching, we are going to approaching birds. Some researchers showed us about the birds. They are saying that when we increase the training images, our test set error drops. So if we want to increase our data and taking more, we cannot take the more images in real life because of we cannot wait the plants grow. So we are using the synthetic data. When we use synthetic data, because of we have a limited images and producing the synthetic data, then when we combine them, we got a problem here. We are saying that reality gap. When we trust with reality gap, we want to decrease this reality gap, and we have to use domain randomization for combining real and fake data properly. So, domain randomization is mixing generating objects over real world scenes. And the other way, GAN actually doing the same thing, fake and real data combining. But we are using this way, domain randomization. Next one, freezing pre-train. We have limited data, but rigid data. When we figure out our data is expressed enough good, important values in the matrix, so we can jump to further more layers. For example, we are start and using one first layer, second, third, etc. But when we are take the good values, we can jump, like residual networks. We are freezing the previous layers and we are starting the middle ones. And the others, RNN and LSTM, related works. RNN, as you can see, a gun. Gun is real data and fake data combining. They are working on the CVPP1 subset data. And LSTM is observing the plans of development and using the leaf shape and inclination angle. Next one. As you can see, domain randomization is using each leaf, for each leaf. And what we are going to do, we are doing the overlaying to real world data. And next one is the inspiration leaf. We are the random deformation, random leaf texture. Think like that. We have encoder, auto encoder. There is a random leaf texture is our bottleneck. We are taking the data. We are using kernel subsampling and taking the more important values. And when we are taking the more important values, we are using the random domain randomization. Yes, domain randomization for each leaf. And overlaying to, as you can see, background is zero black, and we are taking the producing the image, fake image, synthetic image. And actually, this textured leaf is RCNN and segmented leaf showing us mask RCNN. I'm going to next one. Synthetic data generation for, okay. We are taking geometric properties. Inspiration leaf, as you can see before, we are using the inspiration leaf. We use that. Blender deformable object, renderer combining with the real world. When we renderer, using the renderer combining the real world, we choose domain randomization. This is an important thing. And we use the variation from CVPP 30 textures for this research, for this paper. And the next one is actually saying us distribution leaves per image, generate recurrent leaves. This sentence is important. Generate the recurrent leaves is saying us we are using the single plant. We are taking the photos from single plants, top to down, and we are generating fake data. When we send the fake data onto a renderer, we have to use random domain randomization. Random background coming and random camera and lightning coming, they are reaching the renderer and producing the 3D of 2D synthetic image and 2D segmentation mask. As you can see, mask RCNN, 2D segmentation mask. We are taking the ID and we colored them. Next one, we are trying to increase the performance because of, as you can see, we use freezing pre-train. We freeze the previous layers. We are starting to fixed layers maybe. Second one, we are using mask RCNN. And the important things, 500 to 200 regions. interest per image. Interest per image, we are taking the images, and we are hoping that machine learning can debug, decode faster. So this is the increasing performance. And important things, we are using the weights COCOS dataset. As you can see, when we move feed forward, x plus wxi. When we go feed forward, using the feed forward, we are using this equation, and we are using the COCOS dataset weights. So we are changing there, w. And we are using, sorry about that. We are using left, right flipping, top, bottom flipping, rotation, zooming, cropping for the increasing the performance. We are forcing the machine to learn about different situation, in different situation. So we are observing the machine. This machine can learn or not? This machine is giving the true positive or false positive, or false negative. What is our situation? We are forcing the machine to learn. And then, first, they are using the 80% and 80% test data, training data may be different, 20% test data. But when we're combining them, when we're using the renderer side, there, renderer section, we are taking them respectively 50-50 real and synthetic data. And as you can see, we are using the early step for the increasing the performance. Next one, Arabidopsis plants, A0, A2, A4. As you can see, A3 tobacco, A5 all test data. We are taking them producing data to these folders actually. Actually, I want to show that this is saying us, give me the all data from path to data. This star is saying us all of them, and I will output them, producing them these pictures to save folder. So what does that mean? When we run our code, it will produce our data to save folder. A1 output is different, A1, A2, A4, etc. And we are going to result. Result is saying us we have CFA1 real data and their numbers 87, 71, A4, 73. And this is the important things I want to say, that mean per test image performance across all test sets as provided by computation, and not the mean across the table row. This mean is not the average value, average percentage. This is the per image percentage. We are giving the one by one to machine. Synthetic plants, synthetic leaves, 80, 70, 30, tobacco is different things, etc. And finally, we are seeing that synthetic and real data. That was interesting. That is interesting. 90%, 81%, and actually every per image is giving us the 81% in a mean column. And next one is false positive segmentation fiducial marker. Yes, this was an important thing. As you can see, figure A, RGB, we got a fiducial marker, and we are using the, as you can see in C, CVPA1, and we are producing the synthetic leaves from this CVPA1 to synthetic leaf, and finally, when we combine them with the random domain randomization, we are taking the B. As you can see, fiducial marker is gone. Fiducial marker is false positive segmentation. We want to true positive segmentation. If you want to reach this true and positive values from machine, we have to use these steps. CVP, using CVP, LSC, synthetic leaf, and we are combining them with the random randomization. Next one, as you can see, we got a wider synthetic data. That was important because it looks like overfitting there. Taking the more and more values. And in the other end, when we check the real data, we are seeing that more or less than the other synthetic data. Real data is less. When we combine them with the domain randomization, we are taking the best solutions. 90%, and per image is giving us the 81%. Next one is tobacco. We gave the tobacco because of we are checking the machine, what's going on. Machine can figure out the differences between the A3 and the others. Yes, of course, because of the 51% A3. Machine is focusing the Arabidopsis leaves. And then I want to show some samples. As you can see, we can say that A is taking the more values, taking the more data from images and showing that A more wider, taking more synthetic data, and this is the overfitting, but we don't want to use that. When we check the real data side, and we are seeing that not perfect, we need the more sharpened values, we need the more sharpened data from machine. So when we combine them, A and C, we are taking B. When we're taking the B, our solutions are our results, synthetic plus real, 90%, and per images, giving us the 81%. That was a good. And I want to show another sample. As you can see, high bias, low variance is our underfitting side. Low bias, high variance is our overfitting side. And we are trying to catch model complexity, middle of model complexity. As you can see, big M on the graphic, we are trying to catch big M. So what are we gonna do? We are gonna do combine them, real and synthetic data, with domain randomization to determine or figure out the big N. So best solution. And yes, it looks like finished. I am done. Any questions?
Thank you.
Said.
I have a question about that picture that I showed
in slide number 21.
Yes, sir.
I don't understand this picture at all. This is not in the paper. What is the picture of? What kind of picture are you showing here?
Actually, I just want to show a simple, for example, actually. I want to show for example, because of when we take more wider data from the images, as there, we are taking more light, more information from the other world, simplifying actually. Synthetic data is A, real data is C. And when we combine them, we are taking a sharpen, we are taking the more important good results from combining these peaks, A and C. Actually, I want to show, for example, sesim, my voice is coming or not?
Yes, we hear you. Yes, we hear you.
I just want to show, for example, not 100% is proper for this 21 sample.
Said,
I think we got your point.
Thank you.
Thank you. I think I understand what you mean.
Okay, thank you, sir.
Okay,
Okay, maybe we can go on with Melih as our last talk. Melih, are you there? Melih, are you there? Melih is not answering. So maybe I can continue from this point. And should we take a break? Do you think we should take a break? No. Okay, let me continue my lecture then.
So I will share my screen again. Okay, good. And this is where we left. I guess it is what, around 100. Yeah. Okay, so this is the main thing, how we do the captioning. Later they come up with this attention idea. Okay, to tell you about the attention, maybe I should go back and talk a little bit more about. Oh, I am not. Okay, you are not. They are not hearing me. Now you are hearing me, huh? Do you hear me now?
Yes, we do.
Yeah. Okay. Good. So image capturing with attention became very popular, and it is producing very nice results. Let me show you the results first, and let me go back and talk about this. So when you do this, when you give this image to the captioning system, okay, it is supposed to produce a bird flying over a body of water. But while it is producing it, okay, when you say bird, the pixels around the bird is highlighted. It is paying attention to those pixels. When you talk about water is highlighted. Okay. When you say fly again, the bird is flying. Okay, or let's look at this one. When I say a woman is throwing a frisbee in a park, When I say frisbee, the pixels around the frisbee is highlighted. So that's what we mean by attention. And if I do it this way, the final results come back much better than the original idea. But to tell you what attention is actually, maybe I should talk a little bit about encoder-decoder networks a little bit more. Remember our encoder-decoder network? For example, I like eating ice cream. Okay, so I gave this, and I gave this as an input to my RNN network. Okay, and these are all connected. And then encoder-decoder network, then I expect this one to produce dondurma yemeği severim. Okay, so this one will produce this, and this one will produce this. Okay, so but before I produce these words, okay, I am producing some vectors, right? So depending, okay, these vectors are my output vectors, and these vectors produce these words. And the output vectors for this one are usually ignored. I don't care what they are. Okay. So this attention people said this. They say that, okay, during the training, if I am producing this word dondurma, get this vector here, and try to find the most similar vector out of all these four. Okay, so out of all these four, usually what we get is this one. So this dondurma is more similar to this one, and this yemeği is similar to eating, and then severim vector is similar to maybe these two. Okay, so I am calculating automatically an attention matrix while producing these results. I am calculating this attention matrix that kind of ties this yemeği with eating, severim with I like, and dondurma with ice cream. Even though the order is very different from Turkish to English, I can achieve this attention mechanism. And during the runtime, when I am producing something, using this attention idea, I can say that while I am producing this keyword, this Turkish word yemeği, I have eating in my mind. Okay, so that was the attention that they used for the encoder-decoder networks in natural language processing, and later they came up with idea. Why don't we use the same idea with image captioning? While I am producing this, a bird flying over a body of water, why don't I divide this image into these kind of parts, and every time I produce a word, okay, try to see what part of the image is related to that word, and keep that information in your RNN to produce the attention maps too. And that would be the final result. So let me show you the stuff. So I divide my image into smaller parts, smaller features, L times D, okay, in this case 3 by 3. Some CNN stuff. This time it's a specialized CNN because I am not going to talk about the whole image now. I am talking about the parts of it. Okay, and at every time, at every step of my RNN, I am trying to see what parts of the image they are similar to, along with the words. Okay, visual distribution over vocabulary, and do it this way, and using the similar ideas, I can come up with an example like that. We are not doing this just because it looks nice. We are doing this because the results, final results, after doing this captioning with the attention, works very, very well. Okay. So this attention turns out to be very, very useful, very popular, and I think this was around 2015, and starting from 2013-14, attention came into play. Nowadays, everything is about attention. Okay, you heard about this network type transformers. Okay, transformer network, and transformer networks is all about attention. Okay, and there was a very influential paper which is called "Attention is All You Need." Okay, it was talking about the attention for the NLP world. Then later they talked about visual transformer network or visual attention stuff. Now, so we are using it for many different things. Again, the similar stuff could be used for visual question answering. Okay, and visual question answering with attention does much better than that. Okay. Okay, so last week we had a question about, can we have more than one layer of hidden states? And I told you that no, for RNNs usually we don't do that, but if you do, it is possible. If you do, it will be something like this. So this is my input, this is my hidden layer 1, hidden layer 2, hidden layer 3. I have to connect all of them like this in this configuration, and of course there is a set of weight here. Okay, another set of weight, another set of weight, another set of weight. So each circle is another set of weight. Okay, so total of 4, 6, 7 set of weights for this network, and you can have this kind of structure if you would like to use more than one layer. Usually we don't go more than 2, 3 layers. More than one layer, yeah, it is used, but usually we don't go more than 2, 3 layers. I mean, if you think about the CNNs, we are doing rest at 150, etc. We are talking about hundreds of layers. Now we are talking about just 2, 3 layers, and not even 10 layers, which is enough most of the time, because our depth does not come from in this direction. Okay, our depth comes from this direction, in this direction, and if you consider each one as a depth layer, we are talking about hundreds, sometimes thousands of layers. Okay, so let's go back to the original problem. Remember what we said before. RNN has the gradient flow problem. What is it? We take this, okay, internal state and the current input, we put them on top of each other, okay, and we multiply them with this large matrix, and we get our internal state again. That's what we did all the time. But the problem is, every time I go through this path, okay, every time I go through this path, I am running through a layer, and running through layers means that if I do it 10 times or more, during the back propagation, I will run into a vanishing gradient problem. Okay, so vanishing gradient problem will be here. It will go this way. Okay, follow this. Every time I am going over the weights. When you take the derivative of the loss with respect to the weights, I have one set of weight there and another set of weight. Although the weights are the same, I have to take the derivatives of it. So the longer your unrolling of the RNN network, the more weights derivatives you are taking will be a problem. So it will be a vanishing gradient problem. So to solve this vanishing gradient problem, they have invented this network type, LSTM, long short-term memory. Okay. LSTM says that, okay, I will pass two types of information from my set state. One is like the one that used before, okay, HT, and the other one is this, okay. So let's try to see what kind of things they are doing, okay. I is meant for the input gate. It says that I have to learn some stuff from the current input, and I have to forget some stuff from my previous state, and I have to output something from my current state, and G is the one, okay, G is the one that kind of combines some of that information together, okay. So like the RNN, we are doing this recurrency procedures, but unlike the RNN, now we have 4 gates in our cells, okay? 4 different things are happening. We are remembering some stuff from our past. We are forgetting some stuff from our past. We are learning some new stuff from the current input, and we put them all of them together, okay? Learning, okay, forgetting, outputting, and putting them together. So that's what happens with the long short-term memory. So each of these gates, they have their own weights in them, okay. So you have more things to learn, more ways to learn, but it turns out that this works much better than the RNN idea in terms of optimization, in terms of remembering things way from the past. And the main reason for that is this, okay? So this is what's happening. CT minus 1 comes from our previous cell, previous time step, okay? And this is our internal state, comes from the previous cell again. I combine these two and multiply it with 1, 2, 3, 4 different types of weight set, okay. For the output, it has its own weight set. Output cells, they are combined with hyperbolic tangent of the current CT, and they will produce the outputs. F is the forget stuff. See what the F does? Look at this one. F says that I am going to forget some of the inputs, or some of my state, learned state values. So what am I going to do? I will multiply. This is the multiplication operator. It's just pointwise multiplication. It is not vector multiplication, okay? Pointwise multiplication. Since F is a sigmoid operation, it produces numbers between 0 and 1. So zeros are forgotten, ones are kept. In between are kind of stays in between. Okay? So F is for forgetting. I is for inputting. From the current input, again, I is a sigmoid. It is between 0 and 1. I am going to learn some stuff, and it is combined with G. See, G changes from -1 to +1. It is not 0 to 1. So it is adding some stuff from the current state to my final CT values. So if I put many of these together like that, let me take this out. My gradient flow will happen on this top line, on this red line, backward flow. Okay, all the loss values will go back, will go back on this line, and as you see on this line, I don't have any weights. Weights are there. Okay, all I have it is that point multiplication of the vectors and addition, and that's it. So that's the beauty of the LSTM. This one is this one is much better in terms of vanishing gradient problem doing the back propagation training, and as the experiments show, it works much better in terms of its performance. One might say that this looks very much like the ResNet. Okay, remember the ResNet? It has this skip connections between the layers. Okay, so these are your skip connections. LSTMs were invented actually. They were invented way before than ResNet. When they first introduced this ResNet idea, some people said that, okay, all you are doing is just LSTM. You are not doing this in the time dimension or the sequence dimension. You are doing this in the network depth dimension. Okay, so some people agree with this, some people don't agree, and that's what we have. So currently nobody uses RNNs, very rarely used. If you are going to use some sequential data, LSTM is the way to go. Okay, so because it doesn't have any problems that we talked about before. Okay, what else? LSTMs are kind of heavy because you need 4 different types of gates and 4 different types of weight set. So they have introduced this GRU, gated recurrent units. It is similar to LSTMs, but it is lighter. Okay, it has just 3 gates instead of 2, 3, 4. It has just 3 gates. So if you don't have much data to train your LSTM on, instead of using LSTMs, use GRUs. Start from GRU. If it works fine, then continue. Otherwise, switch to LSTM, and you won't be sorry for that. There are other systems that are similar to LSTM or RNN ideas, but basically their ideas is let's keep this gradient flowing during the back propagation, so I don't run into back propagation issues. So in summary, this is what we did. RNNs, okay, they are very flexible in terms of handling sequential data like the natural language processing data or a number of sensor measurements. Okay, our classical RNNs are simple, but they don't work very well in terms of the training. So instead, we prefer using LSTMs and GRUs. Okay, so the problem with the RNN is vanishing gradients, and we can control this with the new idea of LSTMs. Okay, nowadays, as I said before, LSTMs are still being used popularly. LSTMs with attention is used a lot, and we know that it works. And transformer networks actually are the main criticism of LSTM is this. Okay, when you're training an LSTM network, you have to give the sequential data. And if I go back a little bit to the RNNs, if you remember this picture, yeah, remember what we said? I cannot train this like this. Okay, I have to train it with a sliding window. Okay, to train the sliding window, I have to start from the beginning. Okay, let's say I have my Wikipedia data set that contains 2 billion words. To be able to train a character level language model, I have to start from the beginning of the Wikipedia, and by sliding this from left to right, I have to train my network over and over and over again. Yeah, that's one thing. The thing is that this has to be sequential. If I have the CPU power, if I have the GPU power, I cannot do this in parallel. Why? Because I have to start from the beginning. That's the idea of transformer network. Transformer network say that, okay, you take a sample from the middle of the sentences and train it and do this many times, and I can train it much faster if I have the GPUs. And it turns out that transformers are better way of training these kind of systems. They perform much better, but they need lots of GPU time and they need lots of memory, lots of data. Okay, so transformers are actually doing the same thing, but they are not training in sequence. Okay, another thing sometimes, okay, this keyword, this shortened form RNN is used for recurrent neural network. And okay, one of them is recurring neural network. The other one is region neural network. Remember faster RCNN? RCNN, okay. So people sometimes are confused between RNN and RCNN. Okay, they are different. And there is recursive network. Okay, there is a recursive network. What's a recursive network? Again, those recursive networks are called RNNs too. Recursive networks are this. Okay, you keep applying the same network to the appropriate input, and the outputs become inputs to the same network over and over again. Okay, so usually we use these kind of networks. For natural language processing, again, especially for the parsing. Okay, for example, I have this sentence: I read books. Okay, if I'm going to parse it, if I am going to parse this sentence, okay, this is usually parsed like this is verb phrase and this is noun phrase. Put them together, this is a sentence. Okay, so the idea is this: why don't I have a network that can take this too and produce this VP, and the same network that can take this one and produce MP, and the same network will take these two and produce S. Okay, I keep using the same network over and over again until I get the sentence. Okay, so that's the idea of the recursive neural networks. They started very fast. People use them a lot in the early days. Later they just disappeared. So nowadays when they say RNN, they mean recursive neural networks, just opposite. Now they say RNN, they mean recurrent neural networks, not the recursive neural networks. Okay. Okay, I guess that's all the things that I like to say about RNNs and LSTMs. Next week, Yakup Hoca will talk about, I think he will continue, I think he was in the middle of autoencoders, variational encoders, I don't remember. He will continue. And then before the semester ends, I think I will take 2 days to talk about natural language processing a little bit more. And I will talk about attention network transformers, okay? And Yakup Hoca will talk about reinforcement learning and GANs, that kind of stuff. And that will be it. I don't know what happened to Melih. Melih was here, but he left. And next week, we have other people that will talk. Miraj and Ahmed Tugay. Okay. We have 2 speakers for next week. Başak, I don't
Sure.
know. Yes.
I will be there as well, actually.
Excuse me?
We spoke last week, and I will be the third one for the next week.
Oh, okay. Who are you?
And
Who's talking?
Hayrettin Kasım.
Hayrettin Kasım.
Is there anything you want me to cover, especially? I mean, is there anything you say, okay, Kasım, cover this topic, and it's not covered, or should I just bring
Well,
in,
I mean, somebody was going to talk about UNet. Who is going to talk about UNet? I don't see that. Maybe you could talk about UNet now. Oh, somebody got UNet. No, somebody's going to talk about UNet. Maybe talk about object localization, object detection techniques. Start from the RNNs, faster RNNs, YOLO, and at the end talk about maybe pause estimation stuff.
Okay, sir, that will be great.
Okay.
Okay.
Good. Okay. So put your name as the third speaker in our data, in our reservation sheet. And
Okay, sure.
it looks like we will have to hold another, is this the 12th week, really? Okay, we will have to hold another week for the final presentations, maybe. Okay, that's it for today. Thank you, and we will see you next week. I forgot to take the attendance. Bir kağıt çıkarıp imzalayabilir misiniz arkadaşlar?